All right. Let's begin. This is my discussion on chapter 16, monopolistic competition. Of course, the same message applies as before. As always, make sure you go through the details of the chapter. I'm going to go through a few things, especially there are a few things, few derivations here with the typos. So I just wanted to make sure everyone caught those typos. Um, but the rest of this chapter is pretty good and pretty well written. All right, so monopolistic competition. So this is meant to be discussed after you're done with the basic neoclassical model without any distortions. One of the ways in which market power specifically as a distortion is modeled is through monopolistic competition. Um, it is market power and it is a distortion. However, it's also one of the ways in which you as an economist can measure or include in your macro model or your growth model um, increases in welfare through R&D. Okay. And we'll be talking about that very soon in a moment. Monopolistic competition, as opposed to pure monopoly, which we'll just discuss quickly, is actually sort of like a combination of perfect competition and monopoly. And we'll be discussing that in a little bit as to why. But yeah, that is ultimately the point here, that monopolistic competition is, yes, there's a monopoly, meaning prices above marginal cost. However, it is also true that, especially in the model that we have here, average cost is equal to price. So therefore, there is in fact zero economic profits here. Mainly because in this model for monopolistic competition, we have fixed costs of entry, okay, which we'll be talking about in a moment. So first, let's talk a little bit about the microeconomics of monopoly. Don't worry, this is basically just a quick tour of the concept. At the end of this microeconomics of monopoly, we'll just arrive at the notion that a monopolist essentially sets prices greater than marginal cost. That's the idea. And this is essentially the simplest model in which you can arrive at that conclusion or that ending. Okay, so here's a monopolist. You have one firm that supplies the entire market. Okay, therefore, you are not a price taker because you can choose your position along a downward sloping demand curve. So specifically, you have this profit function here, okay, where you have this cost function as a function of Q. You also have a demand function here at some point. It's not here yet. The demand function will be down here. This is at first the perfect competition maximization, because at this point the price is not a function of Q. But for the monopolist, price will be a function of Q because you'll be choosing your position along the demand curve. So we are starting with perfect competition. You get the first derivative of this with respect to Q, and then you'll realize that price equals marginal cost. And this is in fact what has been characterizing our models so far, right? Price equals marginal cost. Now let's contrast this with the monopolist. So the monopolist has an inverse demand curve, this P as a function of Q. It's a downward sloping, and the monopolist can choose Q along the demand curve. So that's why now your maximization problem includes a price, but the price changes depending on what the Q is. You get the first order condition, and if you notice here in the first order condition, it pops out immediately. Price minus marginal cost is still there. So this is the perfect competition component. But the monopolistic component is this one, because as you're increasing in quantity, you're decreasing in price. So this is actually a negative term here. So it lowers your profit if you sell too much, essentially. So here is a force that makes you sell more because as you sell more, you're earning P. But then every time you sell more, that P goes down. So it's a force to reduce your sales. Your marginal revenue is the sum of these two things, the negative thing here and a positive thing here. Okay. Now, mathematically, we have this Q prime times P over Q. Q prime is dQ over dP. So if you write this down, this is going to be your elasticity or the epsilon. This epsilon is your elasticity. Here's your inverse elasticity, which is 1 over epsilon. We will assume here that the epsilon is less than -1. So 1% increase in price level leads to more than 1% decrease in quantity. If you manipulate these equations, you'll see that you can take out the P here and it becomes this expression, 1 over epsilon, and then it becomes 1 over E plus E equals the marginal cost. And therefore, price over marginal cost is just E over 1 plus E. And then you can turn this into this price minus marginal cost over marginal cost. And that'll just be -1 over 1 plus E. So typically, this is not the markup. The markup will be relative to P, but this is another way for you to do the markup when you're dividing it by the marginal cost. So when epsilon is close to -1, you have a bigger markup. And when epsilon approaches negative infinity, the markup goes to 0. Okay, so that makes sense because it's -1 over negative infinity is going to be a very, very small number, and therefore this markup here will go to 0 essentially. This is the example for a linear demand function. Your marginal revenue will be exactly half the slope of your inverse demand. And here's your monopolistic output, and here's your monopolistic price. This is something you might learn in, say, an Econ 11 course, um, or any sort of like managerial or industrial organization class for a first lesson. Okay. All right. So next we'll talk about a macro case, which is like I said, it's an in-between case between between monopoly and perfect competition, and this is called monopolistic competition. Okay. So what is monopolistic competition? It assumes that there are many firms in a market, and that each one um, has a differentiated product. These products are substitutes. Okay. But then there's a degree to which they are substitutable. They are not perfectly substitutable for each other. Okay. A critical assumption is that each firm only considers how setting its price affects its own sales rather than the sales of its competitors. So it does not it has the power to price its own price for its own variety for the product that it's selling, but no thought it gives no thought whatsoever as to what the overall price is. Recall that there are many firms, right, selling different products. So when I'm selling more or less of what my product is, I am potentially affecting everyone else, and I'm effectively forgetting that because I am small relative to everyone else, meaning there are so many other firms, I ignore the effect on the price index or the average price across the economy. Here's an example. Subaru understands at a lower price, they'll sell more cars, but it does not take account as to how this pricing decision will affect the pricing decisions of other sellers of cars, Ford or Honda. Okay. Um, So we make a few simplifying assumptions here. There's only one period. Labor is only the only factor of production. This allows us to ignore capital accumulation and consumption smoothing. We also assume that there is no money or no government spending. Adding any of these ingredients does not significantly change the results. Okay, so we're trying to come up with the simplest monopolistic competition model possible. The household problem is easier than that of chapter 12. The utility function is just a utility function on consumption and leisure. Okay. And your constraint is your consumption has to be equal to your wage income plus your dividend income, which by the way is your total income. This is essentially GDP because GDP is divided into labor income and capital or firm income here. So just as in chapter 12, the household supplies labor up to the point where the marginal rate of substitution for leisure for consumption equals the wage rate, which is this one. And that gives rise to your labor supply curve here, which, as we said, a higher wage leads to more labor being supplied in general. Okay. All right. So this is where we start with monopolistic competition specifically. Here you have many different products Y, right? And it's indexed by J here. So there are many of these J products. And notice that we're using this integral. So if you've done integration before, you'll realize DJ should be like a very, very small interval. Okay. So it's true what the book says. It's like you're adding up all of the different YJs together. But all of the J's are so small because it's an integration operation. Okay. So it's also correct that your interpretation here, the obvious and easy interpretation here would be to treat this as if we were adding up the different Y's. Okay. And there are about M of them. That's what this top integrand upper limit of the integration tells you. Okay. And then the total GDP is basically the sum of all of these different Y's. Okay. And then there's a discussion about what the integral is. In fact, some of the CES presentations out there does not rely on an integration. It relies on just a simple summation. All right. So from now, we'll move to the PowerPoint. Okay. Because um, all of the main derivations I've moved to here. So CES is here is a general CES, like we said. Here are the different varieties, and there are M varieties. Okay. Epsilon here is greater than 1. So this is not the same epsilon as the one in the previous discussion. So epsilon here is greater than 1, and epsilon is a measure of substitutability. T is time, and you can ignore that for now because there's no dynamics in this model as of yet because there's no capital. Okay. The higher the epsilon, the more this ratio becomes equal to 1. Okay. And the more this ratio becomes equal to 1, the more it's as if you're just adding them up, essentially, right? When that happens, if you're adding up the different y's, and that means each, like y1 versus y2, they're perfectly substitutes because they're just, remember the interpretation of a linear utility function or a linear production function, right? All of the different components of that function will then be perfectly substitutable for each other. Okay. So E or epsilon is essentially a measure of that substitutability. And as you'll see, this epsilon will also be a measure of the markup that you're able to charge. By markup, we mean how high the price can be relative to your costs. Sometimes the number of sellers is normalized to 1, which is also happening in the book. So this is normalized to 1. So all of the different YJs are very small fractions, essentially, right? Because if you sum the YJs, ultimately it'll have to be less than 1 because each DJ will be a small fraction of this interval, this difference between 1 and 0. Oops, hold on. Okay, so first we get the first order condition from the maximization of y. So You can consider it a number of ways. So first, the book says that you can consider there is a bundler that sort of bundles all of the different Ys together and bundles it into this Y aggregation here, right? Um, it's true. Another way you can think about it is this is ultimately, yeah, this is Y, correct? If you notice that if this is Y, then this looks almost exactly like a profit max equation. Why? Because this is the total real output, okay? And you're subtracting from it essentially for all the J's, the cost of buying Y, okay? The cost of buying Y. Um, so what this is saying is that, okay, let's try to maximize this expression here. Let's try to, so you can think of this as an intermediate bundler that bundles all of the different Ys. Um, and this is essentially Y, and you're multiplying it by 1 because remember, that's the total revenue that you're getting. And then minus the cost of buying each of these different YJs. So this is a negative number, and it's the cost of buying the different inputs into the aggregation of the bundler. So that's the interpretation of the book. Another way of thinking about it is you can consider this to be essentially um, the consumption of the economy. They're consuming these YJs, and then you're normalizing the price of the total bundle here by 1, and then you're subtracting the cost of acquiring the bundle here. So each J product costs PJYJ, and then you're adding all of the different J's together. And this is the cost of buying all of the different varieties that go into your utility, your total consumption here. Okay. So you can think of it either way works. Um, in fact, a very popular way of motivating CES here would be to use this as essentially your utility function, and this is how you're consuming these goods here, the YJs. All right, so whatever it is, whether you think of this as a bundler that buys all of the different YJs, puts together, sells it for a price of 1, and then this is the cost of buying it. Or you can think of a utility of a household, a representative household buying the Ys, and then this is the cost again of purchasing the different Ys. Either way, you need to sort of maximize this expression here. Okay. So take the derivative with respect to YJT, each variety, and it will become this. Okay, so make sure you're able to try to derive this. This is correct. Okay, notice that this used to be an epsilon over epsilon minus 1. So it's, you know, this is now different, right? And then you're subtracting from this marginal effect, marginal revenue, the price of the variety PJ. Now you can use the definition of Y, which is this one, and notice that this and this are pretty much the same, except that in order to make it 1 over epsilon minus 1, you need to raise this to 1 over epsilon, essentially. And when you do that, you're able to simplify it to this one. So essentially, your demand for the jth variety is negatively related to the price, because it's raised to negative epsilon, but it's positively related to the entire your revenue, essentially, right? Your Y. Okay. Okay. So Y by perfect competition, assume Y is consumed, see in a utility function. Okay. Or you're an aggregator and then you're gonna sell Y. And your price is 1. Okay, because the revenue here is assumed to be equal to your total cost of acquiring the different varieties here, varieties J. Okay. So your total Y, which is again this guy, which is the sum of all the different Yj's essentially, is going to be equal to each Yj times its price, then you're adding it all up. Okay. Which implies, guys, that the price index or the price of Y is 1. Because notice that Y it's basically multiplied by 1 here. And it really should be P times Y equals this, correct? But since there's no P here, clearly the number before YT is 1. Therefore, the price index or the price of the aggregate itself, big Y, is basically this one, right? Where it's the sum of all the sum of all the J's prices raised to 1 minus epsilon. Okay. This derivation, basically, you can get it from the book. Essentially, how do you get from here to here? You use this demand function. See this yj. Yj is a function of this big P, right? And then, this is not big P, but small p. And then you can substitute this y here. So this will just be a function of yt itself and P. And if you notice that there's a YT out here and there's a YT in here, then those YTs cancel and eventually you'll get this one. Which again confirms our idea that the price of big Y is essentially 1, and you can define it as the sum of all of the different or the small p sub jt's. Okay. And this is called the price index of Y. All right, so let's talk about production. Here's your production function for each variety J. Each variety J only uses Nj, that's labor, times A. So A is a common total factor productivity term for every J. Okay. Total cost will be wage times the number of labor that you use to produce Y. And from the production function here, you get this expression Y times W over A, that's your total cost. You can get your marginal cost by getting the derivative of total cost with respect to Y, and it's just the wage over A, which is your productivity of labor. Next is you have your dividend per J. So it's just P times Y minus marginal cost times Y. Okay. So notice that's a common YJ. You can distribute that out if you wish. But remember that Yj is subject to the demand, right? So Yj is essentially a function of P. Okay. So you can plug in this demand function into here, get the derivative with respect to P sub J, and then you'll get something that looks like this. Okay. There's a bit of a typo in the book, so it'll look like something like this. And then the price itself will be this one, which is a function of marginal cost. Okay. And recall that marginal cost, you can replace this marginal cost with W over A if you wish. But it's marginal cost times E over epsilon minus 1. Now, epsilon over epsilon minus 1, what is that? That is a number greater than 1. Okay, that's a number greater than 1, which means that the price exceeds the marginal cost. Okay, and epsilon over epsilon minus 1, that's what's called the markup over price. Okay. Now, this is a distortion because in perfect competition, price should be equal to marginal cost, or price should be equal to W over A. But here it isn't. Price is higher than that because of epsilon over epsilon minus 1. Second observation is the markup is the same for all J's. So there are J different small varieties, but they're all priced the same. Okay? Because each variety is like the same substitutability across all their varieties. And therefore, you have to set the markup as a common markup because all of the different varieties are essentially the same thing, but then they're not perfectly substitutable, which is reflected by the fact that this epsilon is not like infinity. Which again, I guess is the final point. If epsilon here it goes to positive infinity. Then this is positive infinity over positive infinity. That's 1. So the closer you are to perfect competition, the higher the epsilon is. The more substitutable the goods in the bundler or the CES function are, the higher the epsilon here, the higher the epsilon here, the closer this is to like a linear, a true summation of the yj's. And then it becomes perfect substitution, essentially. And all of the prices should be equal to marginal cost. Okay, so there's some aggregation results here. So NJT aggregated across the JT. Notice that the NTs will be the same for all JTs, right? So it'll be the same. So it's not no longer a function of the different J's, right? So each firm will hire the same number of workers, basically, right? And if you continue with this, n times this integral here is just 1, so that's n. And this small n should be equal to big N here. The more interesting result, I believe, is this one. So if you go to your total y, and your total y is defined as the bundling of all the small y's, then you put all the definition of the small y in. Then if you complete this, essentially can remove these an is essentially the same an no matter what the dj's are. So you can remove this, and the summation from 0 to 1 of all of the dj's will essentially be equal to 1. So your y will be equal to a times n, essentially. Okay. So your total GDP is just going to be equal to your total labor endowment times a. Okay. Oops, hold on. Next, here's your price index. And your price index, recall that the price index is essentially a markup over marginal cost. So again, similarly, it has nothing to do with J, right? So all J's will have the same price. You can essentially move this out of the integral. And if you move this out into the integral, it'll become essentially this one. What? This is P. This MC times epsilon over 1 minus epsilon. This is a P, and then P raised to 1 minus epsilon here. And this has to be equal to 1. So therefore, this thing inside has to be equal to 1. And if that's equal to 1, then your marginal cost is epsilon minus 1 over epsilon. So notice your marginal cost is less than 1. Okay, so that's an important result. And recall that your marginal cost is W over A. Okay, so therefore, if this is your marginal cost, therefore your W will be epsilon minus 1 over epsilon times A. Okay, so your real wage should be equal to the marginal product of labor, which is A, right? If you recall, if you get the first derivative of your GDP with respect to labor, it will be A. But now your wage is not equal to the marginal product of labor. It's equal to the marginal product of labor times something which is less than 1. So therefore, compared to perfect competition, your wage will be smaller because you're multiplying something that's less than 1. Here again is an aggregation of consumption, and you'll see that Wn plus D is essentially Y, okay? Because your total, your return to labor, and then this return to capital. But note that there's no capital, so ultimately this Wn will become this An thing here. Okay. So let's talk about efficiency. And again, for our technique here is to solve for the social planner's equilibrium. Here is your utility function. Here is your constraint, C is equal to Y, and your Y is equal to A times N. Here is your social planner equilibrium, which is, again, the ratio of the marginal utility with respect to leisure to marginal utility with respect to consumption should be equal to the marginal product of labor here, which should be equal to W, right? Under the decentralized equilibrium here. However, notice that the W is going to be less than A because of monopolistic competition. So the decentralized equilibrium has lower wages and less labor because of labor supply functions. This will have an implication on the macro labor share of GDP. So let me go to 16.3 and just point things out to you. This should be easy to read. So now we're in this part. Markups in the labor share of income. Now recall that the result of monopolistic competition is less labor. And therefore, if you have less labor, then the labor share of income is uh, clearly going to be less, right? Now, just wanted to point something out. Okay. In contrast, in the model with the monopolistic competition we just outlined, the labor share of income is this. Okay. Implicitly, our production function was with a labor share equal to 1 or a capital share equal to 0, right? So if we generalize this by allowing an alpha, which is less than 1 but greater than 0, so with some capital, it turns out that the labor share in the economy will be 1 minus A, alpha, times this, right? When in a perfectly competitive situation, it should be 1 minus alpha. And recall that this is epsilon minus 1 over epsilon. This is less than 1. So this tells you that the labor share in a more general model with some alpha greater than 0, less than 1, that this will be less than what is in perfect competition because this epsilon minus 1 over epsilon is less than 1. So here is the idea of the fact that labor share is smaller because of market power in the economy. So I invite you to read the rest of this. Clearly, the share of capital will be the following as well. It's alpha times this here, which is epsilon minus 1 over epsilon. Okay, so now we go to endogenous entry. So now instead of having the limit of integration to be 1, now it's m. And m is one of those variables where we're interested in knowing what m is because m is the number of varieties that exist. Okay. So now it's no longer limited to 1. It can go up to some number. It could be higher, right? And the quick question is what determines m? So we use the price index in the definition of price. So essentially go through the same derivation as before. Notice that price is still a function of the markup of over marginal cost. Here's your markup, greater than 1. Then you substitute that into the price, where notice the only difference from before is now instead of 1, it's empty. Then you can manipulate, and then you'll see that marginal cost is epsilon minus 1 over epsilon. And now it's multiplying this m term here, where this used to be 1. Okay. So what this means is your marginal cost goes up as the number of firms or number of varieties go up. Okay. Because you're demanding more and more labor essentially as the number of firms goes up. The same thing with the wage as MT goes up, right? Your wages are also rising because you're increasing your demand for labor, your requirement for labor. Notice that y is not just a function of n of labor, but it's also a positive function of the number of varieties. And this is one of the things I wanted to point out to you that in macroeconomic growth models, you'll have a production function that looks like this. Okay. And then it will essentially boil down to this. Again, I invite you to go through each of these lines for the derivation, but ultimately it will tell you that your GDP will be a positive function of M, or the number of varieties. And that over time, if the number of varieties grows, then your GDP will also be growing essentially. So this one will essentially give you something called increasing returns to scale because as your N is rising, maybe it's growing over time, right? If you recall your solo model, this thing is growing over time. Then this one, M, will also be growing over time here. So it's increasing returns to scale, right? Now, what determines M? Okay, what determines M? Here's your dividend, which is your profit. Okay, and if you manipulate your profit, it will come to this, right? So what it's saying is that your profit, okay, which is actually your operating profit, right, is actually a positive function of M, okay, if epsilon, it depends if epsilon is greater or not than 2. Okay. So it depends on what this is. Okay. Um, what free entry tells you is that your profit now will be your dividends or profit will be this operating profit here, which is PY minus MCY minus some fixed cost F. And then you're equating this to 0. So this is what's called a zero profit condition. So on the right-hand side, you're equating this to 0 here. And now you can solve for M essentially, right? And if you solve for N, it'll result into this situation here. Okay. And if you see, look at the denominator, 2 minus epsilon. Okay. If epsilon is greater than 2, then notice that this one will become a negative number. And therefore, this fraction will essentially flip. The an will no longer be in the denominator, it will be in the numerator. So if epsilon is greater than 2, then an, if you recall, an is y, the number of varieties will be positively related to the size of the economy, which is a times n. Okay. And it will be negatively related to f, which is the fixed cost of introducing a new variety. Okay. So the effects of y equals an on the number of varieties depends on whether epsilon is greater than 2 or not. Okay. And specifically, if epsilon is greater than 2, then more varieties is associated with a higher GDP and a lower cost of entry, or F. All right, so that's it for free entry. That is this part here, section 16.4. Okay. And here's your free entry condition, which is your profits you're going to set this equal to 0 essentially and solve for M. The last part is 16.4.2, which again is the social planner. Okay, so recall this expression for M here is the decentralized expression. So all the firms are doing it on their own, and they don't care about whether it affects much it affects households, right? Okay. However, if you check this out, here is your aggregate resource constraint. On the right-hand side, you have y, okay, which is a times n times the number of varieties here. Okay. Um, although a times n is a measure of market size, okay, which is what I had talked about earlier, how the size of the market will affect the number of varieties here, ultimately. Now, the total output will just be a function of will have to be equal to total consumption. And what's this? F times M. So F times M, this essentially is the amount that you need to introduce this many varieties, right? So ultimately, what this is saying is that your total output should be divided into the amount that you're consuming of the different varieties of the products that's being offered, as well as the cost of actually entering or introducing those costs into the market. Okay, so these are the two sources of your income GDPY here. Okay, so you substitute the C. So this is your C, and notice that the household utility here has the cost of entry as an element. So it's aware that each element or each variety costs F to introduce, right? So it's incorporating that idea into the utility function. Now, the first order conditions are you take the derivative with respect to m, which is the number of varieties, and then with respect to n, which is labor. So if you get it with respect to m, this essentially will become the free entry condition. So notice here, okay, you have this expression here, minus f, and it's equal to 0. And then un will be the usual, right? Expression of the marginal utility of consumption and then the marginal utility of leisure. But the most important part, I guess, for our purposes here is m, which is this equation here, the first one. So if you are able to manipulate that, you get an expression for the optimal number of varieties. Okay, it'll become f over a over n times epsilon minus 1 over 2 minus epsilon. Okay, times e minus 1 times raised to this expression here. You'll notice that this first expression that involves f and a over n should be the same. See that? That's the same. So the expression that includes essentially market size and the fixed cost of entry is essentially the same, but you have this term here, and this term is going to be a function of epsilon minus 1. This one will be different. Okay. Generally speaking, though, m optimal will be bigger than the equilibrium or decentralized equilibrium m equilibrium. If this is true, right? Because that's this one, that's here. And then this e raised to 1 over 2 minus e, that's in the decentralized equilibrium. And if epsilon is very big or big, then the optimal number of varieties here, this expression 16.7, 17, will be larger than the decentralized equilibrium MEQ. Okay. So here's an intuition for the results. Intriguingly, it's not about market power, but it's about the fact that you have increasing returns to scale because it costs F plus MC to produce 1 unit of any of the varieties. Okay. And this is the reason why there is an inefficient equilibrium wherein essentially in a decentralized market, you won't have enough varieties. Okay, you don't have enough entry essentially. You won't have enough new varieties. Okay, but if under the optimal number of varieties under the social planner, it incorporates or it understands that each entry you have to pay an F, and that is included into the analysis, and therefore um, they will increase the number of um, varieties based on that logic. It's the idea that it's aware that each variety requires an F cost, essentially, to introduce into the market. Okay, so there goes the social planner number of varieties versus the social planner decentralized equilibrium, wherein there is a difference between the two, and therefore there is uh, a distortion or an inefficiency with the decentralized equilibrium. All right, and this is where the chapter ends. There's another part here right under this, after this part, about some empirical work on the number of varieties. Feel free to check that out, but that will no longer really be included in the final exam. All right, thank you. See you in a couple of weeks.